All right, welcome to our first test review. The document that hopefully you're looking at is designed to be very helpful for this first exam and give you a strong sense as to the types of questions and concepts and the methodology that I would incorporate to ask you stuff over this first unit. In other words, in a very professional sense, please be very careful about this document and make sure you know how to answer all of these questions. I'm going to go through each and every one and show you how to work them out and what the logic is behind it. And here we go. So for our first question, we have a set of numbers, and our task is to identify whether they're arithmetic, geometric, or neither. Give some sort of reason, figure out the pattern. Looking at 1, 4, 16, 64. So this part we just kind of play with numbers here, so kind of think. If it's arithmetic, then I should be adding the same number each time. So 1 plus 3 would be 4. 4 plus 3 should be 7. So it's not arithmetic. Geometric would mean that I'm multiplying by the same number each time. So 1 times 4 is 4. 4 times 4 is 16. Ooh, I think we got it. And then 4 times 16. Okay, so it is in fact geometric. And the justification is that we are multiplying by 4. So the pattern is to multiply by 4. Is multiply each term by 4. Okay. So then to get our next number, we want 64 times 4. And I am just going to pull up a very weak calculator. So 64 times 4 gives us 256. And then 256 times 4 is 1,024. And then 1,024 times 4 is 4,096. Okay, so there's our first one. Next one, 0, 4, 8, 12. Okay, so if it's arithmetic, that should be adding the same number each time. So 0 to 4, we're going to add 4. 4 to 8, we're adding 4. 8 to 12, we're adding. So it looks like we're adding 4. So it is arithmetic, and we're adding 4 to each term. All right, so if we're adding 4, then 12 plus 4 is 16. 16 plus 4 is 20. 20 plus 4 is 24. So there we go. It's not too bad. All right, and then this last pattern is, let's see, so we'll try arithmetic first. 1 to 8 is 7, but 7 plus 8 is not 27, so it's not that pattern. So it's not arithmetic. Geometric is multiply. So let's see if we're multiplying by 8. 8 times 8 is 64. Okay, so not that. Okay, so this is an example of neither. Oh, wow, what happened there? I'm going to try that again. All right, and neither, and the reason is we're not adding or multiplying each time. Pattern is not based on addition or multiplication. Okay. All right, well now we got to be a little creative and kind of see what do we notice about this. Let's see, so 1 to 8, well, 8, it's not times. Let's see, 8 could be 2 cubed. Let's see, 27, or 4 times 2, so it could be that. 27 is 9 times 3, so that's true. It's also 3 cubed. Oh, I think we noticed something here. 64 is 8 times 8, but it's also 4 cubed. I think we got it. So our pattern is n cubed. So whatever the next, so our next number would be 5 cubed, and then 6 cubed, and then 7 cubed. And so I'm just going to go to a calculator and type that in. Well, actually, 5 cubed is 125. 6 cubed, I don't think we necessarily would know that off the top of our heads, is 216. And 7 cubed is 343. All right, our next skill involves finding the sum of a set of numbers. And this is sort of an application of the Gauss trick from earlier in the chapter 1. And the idea is you add up 51, let's see, 51 to 151. So I'm going to take and I'm going to reverse the order here. So 151 plus 150 plus 149 plus all the way. And if I add those up, I get, what was it, 202 plus 202 plus 202. Okay. So I get 202 times something. Okay, but one of the problems is I don't know, like in order to go from 51 to 151, I'm not quite 100% sure how many terms that is. How many steps did it take to finally get to that number? But we do have a formula that will do that for us. And so this is the nth term of an arithmetic sequence. And so I would make sure you have this memorized because this will come up for this particular topic. And what this formula does is it allows me to figure out what, I've got an arithmetic sequence and I want to know what's the 100th or 150th or 200th term in the pattern. This allows me to see what that particular number would be. So in this case, the nth position is 151. My first position is 51. I don't know n, so I'm going to solve for that. And the only thing I'm missing is my common difference. Well, let me go back to my numbers. If I start at 51 and go to 52 and 52 to 53, what am I adding each time? And hopefully you're catching on that you're adding 1. And then I just need to solve this equation to find my n. So let's see, we'll subtract off the 51, which gives us 100 equals n minus 1. And then we'll add 1 to each side. And so I get that n is 101. So you want to be very careful because I have a lot of students that will tell me that from 51 to 151 it took 100 steps, and it actually took 101 steps. And so that'll affect their final answer. Now let me come back over here. So what we have then is we have 202 plus 202 plus, so we have a bunch of these 202s. How many 202s do we have? We have 101 of them. And remember, I wanted to know 51 to 151 by itself. I ended up adding that twice. And so I actually have twice as much as what I want. And so if I type that in a calculator, 202 times 101 times 2. So 202 times 101 and divide that by 2. That'll tell me what it actually sums up to, so 10,201. And so that's what the answer is for that one. All right, so throughout the course, we're going to have lots of opportunities to demonstrate understanding of the word counterexample. So in this first unit, we're just getting real simple about looking for whether it works or doesn't work. But eventually, we'll want to look for situations where something disproves a particular statement. So in this case, we're told to give a counterexample, and if not, then come up with a way to justify that it works. So the statement is, if two even numbers are added, then their sum is even. Okay, so what I'm going to do is I'm going to just make up two even numbers. So 2 plus 4 gives me 6. And does that match what the sentence is saying? So I've got two even numbers, I add them up, and I get an even number for a sum. So far that works. And now, so here's where it gets tricky is, can we think of a counterexample of this? And so maybe we just start looking at several different examples and see what we end up noticing. So here I just got 3 examples, but notice it's the same observation every time, that no matter what I do, I'm going to add two even numbers together, I'm still going to end up with an even result. Okay, so to sort of justify it or prove it, I'm going to go very generic here, and I'm going to say let A and B be two even numbers. Right? So what would A look like? A is going to look like 2 times some number, and B is going to look like 2 times some other number, and this is for any C and for any D. Okay, relax. Just calm down. I know some of you are freaking out like, where are you pulling this up from? I'm just, in general, okay, if I say something is even, that means 2 goes into it. It means I can multiply 2 times something to generate that number, right? And so if I add A plus B together, well, that's the same as adding this other expression I came up with, so 2C plus 2D. But then notice I can factor a 2 out. Okay, so what have I shown? I've shown that if you in fact add two even numbers together, you're always going to get an even result, that it's always going to be some factor of 2. Okay, so I'll just sort of end this up with a, what do we notice about this? So therefore, any sum of even numbers will be even. Okay. Now, before you stress out about this too much, what actually would be a good answer to this type of question? I was not able to produce a counterexample, and so the question then became, if it's true, then justify it. Give me a reason why, right? And this is the route I chose to go with, was to say, well, let me just pick two even numbers. What does even mean? Okay, it's a very open-ended question. There's a lot of good ways to answer this particular type of question, and there's a lot of bad ways to answer it. This right here, that would not be, so this little chunk, let me kind of highlight this, that would not be sufficient to justify that it works for every case. So I would need a little bit more evidence, or at least some sort of fact or some sort of theorem or some rule that you would be applying, other than saying, well, it works for the numbers I tried, therefore it's got to work for all. In math, that's not sufficient evidence. So just keep in mind, when you see this question on the test, try to come up with a counterexample first, and maybe you can find one and maybe not. And if you can't, then think about a way to sort of formally explain why that observation does work. Okay?